So for the new people who just joined, just ensure that you have your AWS bracket open. Just take a couple of minutes to do that. I'm going to okay, and there's new things on the GitHub, so you can pull stuff from the GitHub too. In the meantime, I'm going to start with a short bit of recap from yesterday on some of the important things that we mentioned today. Okay, the GitHub link. Give me a sec. Let me send it again. Okay. So in okay. So in the meantime, I'm going to start by I'm going to start by recapping a little bit about what we learned yesterday. So a bit of yesterday we learned about two different algorithms. One of them was the one of them was quantum Fourier transform, and the other one was on one of the applications of quantum Fourier transform, the quantum phase estimation. And then I showed about how we could use the quantum phase estimation for to use in short circuit. Yeah. So I just wanted to recap about some of the useful representations uh that you normally see the quantum Fourier transform in. So the first you normally see the QFT for a particular J to be represented in the form of 1 over square root 2n. This is the form that if you are familiar with Fourier transforms, that you're probably going to see a lot a lot more see it a lot more. This is going to look a lot more familiar to you. However, one of the other useful representations that actually would happen a lot, and one that in my opinion is kind of easier to that's kind of easier to see, is that if you represent J, because J here is bit string, so J here is a bit string where you can put J1, J2, J3, dot 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 all the way to Jn, where Ji is in the set of 0 and 1. And so if you write it in this form, this will look like here. It's a product with this, and all the way down tensor product with the okay, actually the brackets. But yeah. Okay. So you will see this form quite a lot if you do play around with the classic quantum algorithms. So do remember both of these representations are both very, very useful. The other thing that we learned in the quantum phase estimation was on this concept called phase kickback. And some of you were having trouble with that idea yesterday. This and I just wanted to kind of go through it a little bit again because it's quite an important concept, especially for this thing especially for Oracle design. Even though QPE was the first time that we introduced this term, the phase kickback. We have actually learned about this during the Dutch-Jozsa algorithm as well. If you remember, during the Dutch-Jozsa algorithm, you started off with I think it was H, and then there was a UF, and this one, if I remember correctly, was the minus state. Might remember wrong. Yeah, minus state. And if you remember at the end of the Dutch algorithm, that we didn't actually need this register anymore. We only measured the first register. I think that's another picture. I might have wrongly, but yeah, that we only measured the first register because we only needed the first register, and we kind of discarded the second register because the second register we didn't really need at all. All this second register that was change the phases of the ones that we wanted. We saw a version of the phase kickback happen during QPE, where when we apply so U is an eigenstate. U is the eigenstate where we apply control U to the power of J. So here to the power of J. So first one was 2. And to this one, I'm just going to put 2 to the power of J, where this one gave us instead something of e to the power of e to the power of I. Just check. Yeah, this one is IUT. No, sorry, this one is 2 to the power of 0 U 1, then plus times that's a product with here times to the power of 1 5 over here dot dot dot. And what the phase kickback did was we could ignore this eigenstate over here. We could ignore this entire thing over here, and all that happened was even though these were the control qubits, the target qubit was the one that was left unaffected. This is going to be a quite important concept for Oracle design. We are going to see it again today during the Provost algorithm. I just want you to just take a note for those of you who are struggling that we can see that this really happens when we are talking about the when we're applying a controlled unitary to an eigenstate of that particular unitary. This is especially apparent for QPE, where we've specified right from the beginning that U and UCAT has basically has this relationship. Has a certain relationship that we want to find. And this was the value that we wanted to find. So we already specified that this had a relationship. So I'm going to just demonstrate 2 simple examples for you, for all of you right now. Okay, about how phase kickback might happen. Or will happen. Okay, so one of them, I'm going to just put 2 registers, and I'm going to put 1 over here. Okay, I'm just going to put the harden here too. Okay, harden the and I'm going to do like a controlled Z gate here. Okay, as I hope you all remember from my lectures and Diction's lectures, that the eigenvalues of the Z gate, is the 0 and the ones. And in this case, we're doing the ones, and the ones that the eigenvalue attached to 1, the eigenvalue attached to 0 is 1, and the eigenvalue attached to 0 cat is 1, and the eigenvalue attached to 1 cat is -1. So now if we to perform this operation over here, where we get this uniform superposition of states, okay, I'm going to separate out the where we perform the uniform superposition of states. So this is this step. I just applied the harder marks to the first two over here. And now we apply the control Z. What? Okay, so maybe it is easier if I do something like this is equals to 1 plus 0, 1, 1 plus 0, 1. Note that I'm separating out the first register and the second. This is the first register and this is second register over here, just for clarity's sake. You can easily write this as 0, 0, 1, 0, 1, 1, 1, 0, 1, and 1, 1, 1 if you wanted. Okay, and now we apply the control Z, which is this gate over here. What will we get for the first term? Can anyone tell me? Oh yes, this is the first time this might be the first time we introduce the multi-control gate. So okay, so yeah, then maybe I won't ask you all for answers. The multi-control gate it has a similar idea to the control gate, where instead of it being you apply this the Z gate here when it's 1. So we remember that if it's not a control gate, so let's say if it's not a control gate, it's just this or particular U, we apply Z when the first, yes, it's like the AND gate on the controls basically. Yeah. So instead of this one we apply Z when this is 1, and we don't apply Z. So this is when we don't apply, and this is when we apply Z. Okay. And when you extend it over here, it means that you don't apply it for 0, 0, 0, 1, and 1, 1, 0, because you want both of them to be ones before you apply it. And so this is the don't apply, and you only apply when it's 1, 1. Okay, so in this particular case, what do I get when if it's 0, 0, do I apply? No. Okay. So I don't apply anything for 0, 0. I don't apply anything for 0, 1. I don't apply anything for 1, 0. But I apply things for 1, 1. And you can see that after you apply the control Z, we can again just take this term out. They take the second register out. Instead, what we get is we manage to apply a phase change for one of the terms in the first register, so in the first 2 qubits. And It's for the one we wanted. Oh, well, for the one that this particular term kind of showed. If we manage to apply for a phase change for one of them that we specified. And I think the fun part to note about this is that this is not there's not only one way to do this. And so I say I show two examples. Now I'm going to show you all a second example to just drive home the point about about applying it for controlled versions of uh the eigenvalues and eigenvectors. So instead now I'm going to do the minus state over here. I'm again going to do the uniform superposition of states. But instead, this time, I'm going to do the CCX gate, which is another way of saying CC naught. Okay. So let's see what happens. So we know that this is here, and I'm going to write this instead in this form. Maybe I hope you all can see. Okay. I'm omitting the constants in front of it because I'm lazy and it's not really that relevant. Plus 1 1. So now when we apply the CC not gate to this, what do we get for the first term? Does anything happen to the first term over here? No. Great. Yes. So first term remains the same. Second term, I hope you all can see that it remains exactly the same. Third term remains the same because we don't apply anything. And last term, what happens to it? What's over here? So something happens here. What happens? Mm. The 0 and the 1 swaps phases, right? Okay, so can you all see that if the 0 and 1 swaps phases, so it's which is makes this minus 0 plus 1. And this is basically minus 0 minus 1. And this minus comes out here. We can bring out the minus here. And so what we get at the end of the day is 0 0 plus 0 1 plus 1 0 minus 1 1. And in this case, this remains exactly the same. The minus state. Okay, why is this so? We remember that I said that this only happened because the eigenvalue, for the Z gate, the eigenvector and the corresponding eigenvectors, one of them is the zero cat, and one of them is the 1 cat. And the corresponding eigenvalues are 1 and minus 1. In this particular case, for the X gate, for the bit flip, the corresponding eigenvectors for it is actually the plus state and the minus state. and the eigenvalues for them is 1 and -1, which is why this phase was applied which is why this phase was applied. Okay, so this is, I hope that you all can see a bit more clearly, or you all understand a bit more clearly on how phase kickbacks works. We see that I've just shown two examples of basically how you can perform phase kickback. About how phase kickback have seen you can see it in both like the Z gates and for the CCZ, the Z gate and the X gate with showing the eigenvectors and the eigenvalues. And I hope that you can see how this applies for QPE, how the phase does not necessarily need to just be -1 or just be -1, but it can be any phase that you kind of put to it over here, as long as eigenvalues kind of correspond to that. So technically, if instead of the minus cat over here, you do the plus cat over here, you could technically induce phase kickback as well, but what you'll be changing the phase to is just multiplying it by a factor of 1, which basically does nothing. So yeah, that's kind of like a short a short-ish description of what phase kickback is. Okay, so now that we are done with okay, so at this point, does anyone have any questions? Yeah, before I jump into Grover's. Okay. I don't see. Okay. Can multi-control gates be decomposed into multiple gates? Yes. Yes, they can. So, okay, so this is quite an important question, actually. We see that multi-control gates are basically are in this particular case, these are 3-qubit gates. You can have some 3-qubit gates. You can have some gates that are like n-qubit gates if you wanted to. Those are theoretically possible. And so this becomes an important kind of question about circuit design, because decomposing a 3-qubit gate, you want to be able to decompose almost any operation you want to apply into 1-qubit gates, 1-qubit gates and 2-qubit gates. Why you want to decompose things into 1-qubit gates into 2-qubit gates is because when you build a quantum computer, you are really only going to build functions you're really only going to build functions that a limited set of functions that you can then apply a lot of things for. If I were to do a classical analogy to it, a classical computer analogy, you realize that most of your logic functions are basically just made up of your AND, NOT, and OR. It doesn't really go beyond. It doesn't. More you can kind of decompose almost any logic function into those few, if I remember it correctly. In this particular case, you realize that you'll be able to there are some theorems out there that state that with certain gates, you're able to get extremely close to almost any multi-qubit gate possible. And these are what we call universal gate sets. The smallest universal gate set is actually a 4 uh it's a four has four gates in it. There's identity, the identity gate, the halaman gate, the T gate, and the C naught gate. We see that these are the 1 qubit gates. I should have done it the other way. These are the 1 qubit gates, and this is the 2 qubit gate. So generally, this is not how things are going to be implemented inside the actual quantum computer. Generally, what happens inside a quantum computer is that you apply quite a number. You Oh, the T gate, yeah. So the T gate, I think is basically if in the unitary form, I think it's e to the power of I pi over 8, pi over 8, pi over 4. Is it a pi over 8 or pi over 4? I kind of yeah. I've kind of forgotten. There's that you can probably, yeah, pi over 4. Yes. Yeah. Just off the top of my head. So the T gate is that generally you what generally 1 qubit gates are cheap to implement. And so if you go and take a look at IBM, you see that actually they'll implement identity, Hadamard, I think RX, RZ, something like that, and plus, and then they'll add one 2 qubit gate, and the 2 qubit gate is generally either C naught or CZ. Yeah, because 1 qubit gates are kind of cheap to, or rotations are particularly sometimes quite cheap to implement, so they can do it for they can do that, and so the decomposition becomes a lot easier when you don't have to care about just one phase, when you don't have to just work on everything based on one phase. It becomes a lot cheaper to do things, and so this is generally how it's applied. And so the multi-control qubit gates that you will see, the multi-control gates be decomposed to multiple gates. It's actually almost it's not just can it be decomposed, it's necessary for it to be decomposed into multiple gates, into multiple 1 qubit and 2 qubit gates, so that it can actually be implemented on a quantum computer. Okay, the next question obviously comes in terms of circuit design. You want to kind of especially the particularly expensive, you especially the ones that have n qubits, you want to implement a smart way of kind of decomposing into multiple gates. If you can use less gates, that will always be ideal, because it will take less time, and it'll be less noisy. Especially, and then the second point is especially relevant for today during the not when quantum computers are all like inundated with noise. And so that becomes under that kind of goes under circuit transpilation. If you can go and take a look at circuit transpilation, there's this whole part, or this whole area of research where it's like, how do we decompose the circuits in a smart way into its basis gates? Okay, that was a really good question. Does anyone else have any questions? Is there any systematic way to do these decompositions? Yes. There are quite a few systematic ways of doing these decompositions. I'm not really going to get into that right now, because that's so this is an active area. This is a really active area of research. There are many ways to optimize doing these circuit decompositions, and it's quite it can get really technical. The Most of the time, people so there's been I can tell you a few schools of thoughts about how things have developed. Uh, yeah, I can tell you a few school of thoughts about how things have developed over time. So first, during the early days of quantum computing, people were the main metric that people were going by for decompositions of for doing this systematic for doing these decompositions were kind of like trying to reduce the circuit depth as much as possible, and so they're worrying about the number of gates that they applied. Nowadays, because we realize that the 1 qubit gates are actually a lot cleaner than the 2 qubit gates, people have started focusing their efforts on creating systematic ways of doing these decompositions that limit, instead of just the number of gates, limit the number of 2 qubit gates that we apply, because they realize that this is a smarter way of doing this. In particular, these decompositions are particularly difficult. Creating systematic ways of performing these decompositions are particularly difficult because many quantum computers nowadays have limited topology. I'll be getting into that a little bit later. I will be getting into that a little bit later for the different topologies, but basically not every gate can be just C-naughted to one another very easily, and you have to perform a number of swap gates, which each swap gate, as you had learned from Dikshan I think yesterday or the day before, is basically 3 C-naught gates, and so that's three 2 qubit gates that you apply. Okay, yeah. Pascal's point is also very important. There are many emulators for it, and it's important to test an algorithm on the emulator. You want to see how it performs perfectly, and then you want to try to implement a noise model for these time. You want to implement a noise model, especially if you're doing especially if you're doing a project net to if you want to see how it runs on the quantum computer. It's uh you it all comes under you I a good place to start looking at it is just to start looking at this thing called circuit transpilation. I would you all can Google things. You can Google things on that. This is a huge area of research as well. I think one of the IBM uses this circuit transpilation for their optimization level 3 called Saber Swap. That's one, and there's like a 20-page paper on this circuit transpilation into decomposition into basis case kind of works sometimes for them. Yeah. And so there are many systematics. Yeah. Yeah. It is important to dive into transpilation when you run on real hardware. And so it's not only circuit decomposition you have to worry about, there's a whole list of things that you have to worry about. And so which is if you're interested in it, I recommend you all start looking at the different ways people do circuit transpilation and Saber swap, I think. So this is just kind of off the top of my head. Saber is definitely part of Saber is definitely part of the name. I might have gotten the second part of the name wrong, but yeah. This is what IBM uses for the highest optimization level. It's also particularly interesting because sometimes they're doing approximations rather than actually just getting the exact circuit out, and that's a sacrifice sometimes that they decide to make that they decide to make in order to ensure that they have as low a circuit depth as possible. Oh well, a 2 qubit circuit depth as possible. I think that's the case for Saber Swap. Okay, so some really great questions coming up. Any more questions? What motivates this problem in 2 quantum registers rather than one larger? Uh, So I assume this problem is in terms of phase kickback. Uh, this problem refers to phase kickback, right? Just to clarify before I go. The last problem that we did yesterday. Quantum phase estimation. So what motivate representing the problem in two quantum registers instead of one larger quantum register is the same reason as why we kind of did things why we did things in two quantum registers here today. You notice that I kind of separated things out into this first register, into this second register. Because the second register is really that because it's kind of like the first register is what we're interested in measuring. The second register is a workspace. Is sometimes so you notice this term sometimes when you read papers called ancillary workspace. You will see these terms. You see these terms and these terms in textbooks. You see these terms in papers. This is basically the second register is generally just this thing called what we call an ancillary workspace, where you implement certain states that help you in the help you in the circuit and the measurements that you actually want to perform. So in the case of quantum phase estimation, in the case of quantum phase estimation, I think I do in the quantum phase estimation over here, where you can have 0 dot 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 over here, and all these go down a bit more. You realize that the important part, what we're measuring, is only the first register. We only measure this part. And we don't care about the second register as well. The second register has done its job. The second register is there for us to help us to perform our phase kickback, and then we ignore it after that. We just measure the first register. So this is what we're interested in. This is the ancillary workspace. And this is what motivates us in representing this problem into quantum registers, because certain parts or certain qubits are what we're interested in, and certain qubits are there just for us so that we can perform stuff on the qubits that we're actually interested in. And so representing it in two different quantum registers is just kind of like, division of labor over here. It just helps us to separate things out into two. It helps separate things out so that we can understand things a little, so that we can understand what is happening a little bit better. In this particular case, ancillary workspace is help us to perform phase kickback, and then we measure things on the qubits we're actually interested in. Okay. Does that answer your question? Yes. Okay. Great. Many good questions coming up. Okay. So in the interest of time, so we are really, really over time, but I think it's good that we are kind of I think it's good that we are kind of clearing up a lot of these questions. Okay. The phase kickback will be important for today. So I'm going to proceed to the lecture on Grovers now. Feel free to ask more questions. I will try to answer them as much as possible.